Welcome to lecture 6.4, Galois groups. A few slides ago, we learned about the Galois group of a field extension of Q, and to refresh your memory, that was just the automorphism group of that field. And now we're going to turn our attention to the Galois group of a polynomial. So let's suppose that f is a polynomial with integer coefficients. Now it could have rational coefficients, but if it does, we usually just multiply by the LCM of all of the coefficients, and it gets something with integer coefficients. And that doesn't change the roots. So let's just assume that the coefficients are integers, and the roots are R1 up to Rn. Now these are complex roots, or they could be. They might be irrational, they might be imaginary, we don't know. Doesn't matter. Then the splitting field of f is, by definition, the field Q, the rationals, adjoined all of those roots. So it is the smallest extension field of Q that contains all of the roots of the polynomial. Now, the splitting field, let's call it capital F of the polynomial little f, has several equivalent characterizations. First, as I said, it's the smallest field, or the smallest extension field of Q that contains all of the roots of the polynomial. Or equivalently, it's the smallest field, again, extension field of Q, in which the polynomial splits into linear factors. And by splits, I just mean it breaks up, or it factors into linear factors like this. And this can only happen if all of these roots, R1, R2 up to Rn, are in the field itself. Now, something that I said earlier, recall that the Galois group of an extension of Q is the group of automorphisms of that extension, and we write that as Gal of F. We usually just say the Galois group of F. In a similar vein, we can define the Galois group of a polynomial to be the Galois group of its splitting field, and we denote it similarly Gal of F of x. Let's do some examples of Galois groups of polynomials. Now, a few lectures ago, we did examples of Galois groups of splitting fields, and we didn't prove all of our claims, but we did it in enough detail that hopefully it was convincing and enough to get the intuition. So let's begin with the polynomial x squared minus 2, and this splits in the extension field Q adjoined root 2. So the Galois group of x squared minus 2 is the Galois group of the splitting field Q adjoined root 2, and I claim that's isomorphic to C2. Now, here's a sketch of why that is. So consider the automorphism that sends root 2 to negative root 2. Recall that that is an automorphism of this field. And then we have the identity automorphism as well. And those are, in fact, the only two automorphisms. And so the Galois group has order 2, and so up to isomorphism, it has to be C2. Next, the polynomial x squared plus 1 splits in the field Q adjoined I. So very similar to the last one, the Galois group of this polynomial is the Galois group of Q adjoined I, and here we have one non-trivial automorphism, which sends I to negative I. It's just complex conjugation. And so if we have a group of two automorphisms, then it has to be isomorphic to the C2, which is the only group of order 2. Next, the polynomial x squared plus x plus 1. Recall that has two complex roots, and it splits in Q adjoined zeta, where zeta is a primitive third root of unity. Now recall that if this is a unit circle, then zeta is up here, and its complex conjugate, zeta squared, is down there. And again, there are only two automorphisms of this field. In this case, the non-trivial automorphism sends zeta to zeta bar, which is just zeta squared. So, as before, the Galois group has two automorphisms. It's isomorphic to C2. Next, the polynomial x cubed minus 1. This factors partially. So it factors, but it doesn't split. So it's x minus 1 times x squared plus x plus 1. So in order for this to split, we have to go into Q adjoined zeta, as in the previous example. So the Galois group of this polynomial is the Galois group of the splitting field, which is the field that we just saw in the previous example. So that also has to be isomorphic to C2. Next example. Let's take the polynomial x to the fourth minus x squared minus 2. This factors as x squared minus 2 times x squared plus 1. So it factors into two irreducible components. And in order for this to split, you have to go all the way up to Q adjoin root 2 and I, because the roots here are plus or minus root 2 and plus or minus I. So you have to adjoin both of these. So the Galois group of this polynomial is the Galois group of this field extension, Q adjoined root 2 and I claim that that is isomorphic to V4. And to see why, let me show you what the non-trivial automorphisms are. Well, there's one of them that sends root 2 to negative root 2 and fixes I. Then there's another automorphism that fixes root 2 and it sends I to negative I, so complex conjugation. And finally, there's an automorphism that flips both of these, so it sends root 2 to negative root 2 and I to negative I. So if we call this first automorphism, let's call it H, and we call this next automorphism V, then this last automorphism is H times V. It's what we get by doing these two automorphisms in either order. So it's not too hard to check that these are in fact the only automorphisms of the splitting field. And therefore the Galois group of this splitting field and thus of this polynomial is isomorphic to V4. Next example is very similar to the previous one. The polynomial x to the fourth minus 5x squared plus 6. This factors into two irreducible components, x squared minus 2 and x squared minus 3. And so it splits in the field Q adjoined root 2 and root 3. So the Galois group of this polynomial is the Galois group of the splitting field, Q adjoined root 2 and root 3. And very similar to the previous example, there are four automorphisms, and this is isomorphic to V4. One automorphism sends root 2 to negative root 2. Another one sends root 3 to negative root 3. And then there's the one that does both of those. So I'm not going to write this one out because we will do it in more detail later in this lecture. Finally, the polynomial x cubed minus 2, that splits in the field Q adjoin zeta and the cube root of 2. And as before, zeta is a primitive third root of unity, e to the 2 pi I over 3. And so the Galois group of this polynomial is the Galois group of the splitting field. And we've given evidence previously to suggest that this Galois group should be isomorphic to D3, the dihedral group. And the evidence was of the form of the subfield lattice of this field looking just like the subgroup lattice of D3. Now I didn't prove anything about that correspondence, but I pointed it out, and so that should give enough evidence that hopefully you believe that the Galois group is isomorphic to D3, but this is something that we will establish firmly later in this lecture. Before we can do any of that, we need to establish a basic property of field extensions, which is very similar to a basic property of subgroups that we have already seen. Recall that if we had a chain of subgroups, so K is contained in H, which is contained in G, then the index, recall the index of a subgroup H in G is the number of cosets that it has. The index satisfies a Tower law, namely the index of K in G is the index of H in G times the index of K in H. And a way to prove this by a picture, and I say prove in quotes, is, well, if this is the subgroup H, and then we look at its cosets, x, h, let's do left cosets, y, h, and so forth. And then k is a subgroup of h. Let's say k is, this is k. So the cosets of k and h are like ak. Actually, let me call this not ak. Let me call this h1k and h2k and h3k and so forth. So the number of cosets of k in G is just the number. So that's this number, the number of cosets of k and G. That's the product. It's the number of cosets of k and H, which is this. This is how many cosets of k in this little rectangle are there? Well, there's h, the index of k and h, and then multiply that by the number of cosets of h in G, which is the number of these boxes, and that's how you get the number of these small boxes, these cosets of k in G. So that was the picture proof of this. Now, of course, you need to do it formally, especially if you have something like groups of infinite size. Okay, so back to fields. Not surprisingly, the degree of field extensions obeys a similar Tower law. And for any chain of field extensions, so suppose f is contained in E, which is contained in K, then the degree of f in K is equal to the degree of E in K times the degree of f in E. And I say not surprisingly because we've seen this. Well, at least we've seen that subgroup lattices and subfield lattices look similar. And let me give you an example. So let's consider, say, Q adjoined root 2 and root 3. This has 3 non-trivial subfields, Q adjoined root 2, Q adjoined root 6, which is the product of root 2 and root 3, and Q adjoined root 3. These are all, of course, these all contain Q. So here is the lattice of subfields, and each extension here has degree 2. Now the Galois group of this field is isomorphic to V4. So let me write V4, which is generated by H and V. And the subgroups of V4, there are 3 of them that are non-trivial. The subgroup generated by H, the subgroup generated by V, and the subgroup generated by HV. These are all contained in the trivial subgroup, of course. And these subgroups all have index 2 in the subgroup directly above them. And now we've observed that these lattices are going to be identical, well, if we turn one of them upside down, although in this case that doesn't matter because there is symmetry on the top and bottom. So my comment of not surprisingly is motivated by the observation that these edge labels here are the degree of the extensions on the field side, and they are the index of the subgroups in the group side. So in the group side, we know that the index of this subgroup in that one is just the product of these labels, 2 times 2. So over on the field side, the degree of this extension over that one should also be 2 times 2. Let me write this up formally now instead of just pictures. So the degree of the field extension, Q adjoined root 2 and root 3 over Q, is equal to the product of the degree of Q adjoined root 2 and root 3 over Q adjoined root 2 times the degree of Q adjoined root 2 over Q. And each of these has degree 2 because each of these fields, these extension fields, are achieved by adjoining the root of a degree 2 polynomial. So, namely, starting at Q, if you adjoin a root of x squared minus 2, you get Q adjoined root 2. And then from here, if you adjoined a root of x squared minus 3, you get the big field. So the degree of this extension is 2 times 2, which is equal to 4. Here's another example. Q adjoined zeta and the cube root of 2 over q. By the Tower law, we can break this up, and let me start with the right-hand term. Start with q, and adjoined the cube root of 2, and that is a root of a degree 3 polynomial, and so this is a degree 3 extension. And then from this subfield, we need to adjoin zeta to get to our big field, and that is a root of a degree 2 polynomial. So the degree of this extension is just 2 times 3, which is 6. And that brings us to the concept of a primitive element and a result that I like to call the primitive element theorem. This says if f is an extension field of Q of finite degree, then f has a primitive element, which is some number for which the field extension f is just Q adjoined that number. Now such a field extension, Q adjoined a single element, is said to be simple. So what this says is that every finite degree extension of Q is simple. In other words, it has a primitive element. Let's do an example to make sure that we fully understand this concept and what it's saying. So I want to ask, how do we find a primitive element alpha of the following field extension? That is Q adjoined zeta and the cube root of 2. So we know that this field extension, Q adjoined zeta and the cube root of 2, has degree 6 over Q. So by the primitive element theorem, there is an irrational number alpha for which this field extension is equal to Q adjoined alpha. And I'm asking you, how do you find such an alpha? Because it's not necessarily clear that if we adjoin these two elements separately, that we could have done that with just one. So to help, I'm going to write this field extension, Q adjoined zeta and the cube root of 2, slightly differently. Q adjoined I root 3, which, by the way, I root 3, recall, is equal to the square root of negative 3. So Q adjoined root negative 3 and the cube root of 2 is another way to write this extension, and that's something that we saw a few lectures ago. So I'm going to propose an idea for the primitive element, and we will show that it works. Well, let's try alpha equals I root 3 times the cube root of 2. So we are taking the product of these two elements together. Clearly, the degree of Q adjoin alpha over Q is at most 6, because we know that Q adjoin alpha is a subset or a subfield of this extension. And if it's the entire extension, then we've found our primitive element and the degree is exactly 6. However, if it's a proper subfield of this, then the degree is less than 6. So it's not hard to check that if we take successive powers of alpha, we get that alpha squared is negative 3 times the cube root of 4. Alpha cubed is negative 6i root 3. Alpha 4 is negative 18 cube root of 2. And alpha 5 is 18i cube root of 4 times root 3. And most importantly, alpha to the 6th is negative 108. So this is the one that we care about the most because it tells us that alpha is a root of the polynomial x to the 6th plus 108. Great. So where do we go from here? I claim that the following are equivalent, and I want to make sure that you understand why. Now we know enough math so far to understand, but you just have to apply it. The first condition is that alpha is a primitive element of f. Now that happens if and only if the degree of the extension of Q adjoin alpha over Q is equal to 6. Remember that argument? We said Q adjoin alpha is equal to the entire field if and only if the degree is exactly 6. So that's what the equivalence of these two statements is saying. Next, the minimal polynomial m of x of alpha has degree 6. Recall from the previous lecture that the degree of an extension like this is equal to the degree of the minimal polynomial of alpha. So if the minimal polynomial of alpha has degree 6, then that is the same thing as saying this field extension has degree exactly 6. Finally, the last condition is that x to the 6 plus 108, that is this polynomial right here, is irreducible. Now recall that the minimal polynomial, by definition, is the smallest degree polynomial of which alpha is a root of, and it is irreducible by definition. So if this polynomial is irreducible, then it is the minimal polynomial m of x, and this field extension has degree 6, and therefore alpha is primitive. Conversely, if this polynomial is not irreducible, then it breaks up into a factor of a product of two smaller degree polynomials, and alpha has to be a root of one of those polynomials. If that's the case, then the minimal polynomial m of x of alpha has degree strictly less than 6, which means this field extension has degree less than 6, so alpha is not primitive, because in that case this field extension would not be equal to the entire field extension q adjoins zeta and cube root of 2. Okay, so you got this? This is what we're trying to prove, that any of these statements hold. So how do we do this? Well, let's start with x to the 6 plus 108. We have a very simple test for irreducibility. It's Eisenstein's criteria. Remember that? So it says if there is a prime number that divides all of the coefficients of this polynomial except the leading one, which is 1, and the polynomial, and the prime p squared does not divide 108, then we're done. Our polynomial is irreducible. So 108 actually is equal, what is it, 12 times 9? So that means it is equal to 2 squared times 3 cubed. And unfortunately, there is no such prime p that divides 108 such that p squared does not divide 108. So that doesn't tell us that this polynomial is reducible. It just tells us that Eisenstein's criterion doesn't work. It doesn't give us any information. So unfortunately, the thing that we seemed like it could work doesn't work. So we have to try to prove one of these three conditions instead. And we will actually prove this second condition by using the Tower law. In fact, the reason why the degree of this extension is equal to 6 is because both 2 and 3 divide it, as can be shown relatively easy from the Tower law. By the Tower law, I claim that the degree of q adjoint alpha over q is just this product here. Although before I can actually say that, I need to establish that this subfield, q adjoint I root 3, is indeed a subfield of q adjoint alpha. Otherwise, the statement doesn't make sense. And to see that, I claim that we can generate I root 3 from alpha. So notice that alpha cubed is negative 6i root 3, and therefore alpha cubed divided by negative 6 is I root 3, which is contained in q adjoined I root 3, and therefore this must be a subfield of q adjoined alpha, because from alpha we created this element, and thus we can create everything in this field. So because of that, we can apply the Tower law, and so this product is, this has degree Well, we don't know what degree this is, but we know this is degree 2, and therefore 2 divides this total degree. Next, Q adjoin alpha over Q we can break up differently. We can break up like this, as long as Q adjoin cube root of 2 is a subfield of Q of alpha. So why does that work? Well, now let's look at this relation. Alpha to the 4 is equal to negative 18 cube root of 2. So in other words, alpha to the 4th over negative 18 is the cube root of 2, which is contained in Q adjoined the cube root of 2. So that must be a subfield of Q adjoin alpha, because using our only generator of this field, we can create the cube root of 2. Therefore, we can apply the Tower law like this, and so this, whatever integer this is, has to be a multiple of 3, and we also know it's a multiple of 2, and therefore it has to be at least 6. And we've already proven that it has to be less than or equal to 6, and together that means that the degree of this extension is equal to 6, and therefore alpha is indeed a primitive element. We will conclude this lecture with one example, which we touched on briefly in the second slide. This is the Galois group of the polynomial x to the 4th minus 5x squared plus 6. Now this factors into two irreducible products, and so the splitting field of this polynomial is Q adjoin root 2 and root 3. We already know that the Galois group of this polynomial should be isomorphic to V4. But let's compute it explicitly, and this will help us understand it better. Now we need to determine all automorphisms of this splitting field, because that's, by definition, the Galois group of the polynomial. We know that an automorphism phi is determined by where it sends the basis elements. So where it sends 1, root 2, root 3, and root 6. We know it fixes 1 because it must fix every rational number. Also, if we know where phi sends 2 of these 3 radicals, root 2, root 3, and root 6, then we know where it sends the third. Because by the properties of homomorphism, phi of root 6 is just phi of root 2 times root 3, which is phi of root 2 times root 3. So if we know 2 out of 3 of these things, then by the fact that they are equal, we can deduce the third. Now, in addition to the identity automorphism, which we always have, we have the following non-trivial automorphisms. We have phi 2, which sends root 2 to negative root 2 and fixes root 3. We have phi 3, which fixes root 2 and sends root 3 to negative root 3. And then we have phi 4, which is just the product of these two automorphisms in either order. So it swaps the sign of root 2 and root 3. Let me ask you a question, something you might be wondering. What goes wrong if we try to force the condition that phi sends root 2 to root 3? Why does that not generate an automorphism? And this is something that I will encourage you to do on your own. I think it might be on the homework, but I'll give you a hint. It's a pretty big hint too. So phi of 2 we know has to be equal to 2, right? We can also write this as phi of root 2 times root 2, which is phi of root 2 times phi of root 2. So what if phi of root 2 equaled root 3? Well, I said you would do this on your own, but I've pretty much given it away now. Suppose phi of root 2 were equal to root 3. Well, then we could write this as root 3 times root 3, which is equal to 3. But we also know it's equal to 2. So that's not possible. In summary, there are 4 automorphisms of the field Q adjoined root 2 and root 3 which is the splitting field of this polynomial. The identity fixes everything, and now recall that an arbitrary element of this field has the following form: a plus b root 2 plus c root 3 plus d root 6. So the identity does nothing. Phi2 fixes a. It swaps the sign of b, so b root 2 gets sent to negative b2. It fixes root 3, and it swaps the sign of root 6. And that is because phi2 of root 6 equals phi2 of root 2 times phi2 of root 3. And phi2 of root 2 is negative root 2, phi2 of root 3 is positive root 3, so we get negative root 2 times root 3, which is negative root 6. Next, phi3 swaps the sign of root 3, and thereby doing the same thing in front of root 6. And finally, phi4, which is what you get when you do root 2 and then root 3 in either order, swaps the sign in front of both root 2 and root 3, and it does it twice in front of root 6, so it preserves that sign. These four automorphisms form the Galois group of our polynomial, and the multiplication table and Cayley diagram are shown below. So from here, it is easy to see that this automorphism group is isomorphic to the Klein 4 group V4. So here's the multiplication table, here's the Cayley diagram, and here is a picture of the four roots of the polynomial in the complex plane with arrows showing what happens when you apply the automorphism phi2, swaps root 2 and negative root 2, and phi3, which swaps root 3 and negative root 3. This is foreshadowing. This is what we will study in the next lecture. This is the action diagram of a group action. Specifically, let's take our set S to be the roots of the polynomial. So we have plus or minus root 2 and plus or minus root 3. So we have a 4-element set. And the Galois group acts on this set. Now that's not clear, that's not obvious. We have not proven that if we take an automorphism of a root of a polynomial, then we will get a different root of a polynomial. But that is a basic fact that we will uncover in the next lecture. And as a consequence, it means that the Galois group naturally acts on the set of roots. So here is the action diagram. It has two orbits, in other words, two connected components, the red one and the blue one, and it has no fixed points. We will learn all about this action and its properties in the next lecture. But for now, I want to leave you with an exercise, something to think about. I want you to try to show that this alpha, so alpha is root 2 plus root 3, is a primitive element of this splitting field. In other words, if you start with q and you adjoin root 2 plus root 3, then you get exactly the same thing as if you adjoin root 2 and root 3 separately. So you get a degree 4 extension. So think about how you would do that, and my hint is that it's not too much different than the example that we saw previously, where we took alpha to be root negative 3 times the third root of 2, and we had to show that this was a primitive element for the field extension q adjoined zeta and the cube root of 2. Okay, good luck.